Welcome to lecture number 7 of module 3. In this lecture onwards, I will be discussing about the voltage control. In the previous lecture from 1 to 6, we saw the modeling and how the frequency will be controlled of the system. So the voltage control basically related with the reactive power control, means the reactive power and the voltage both are related to each other. Now let us see that how a generator can control your frequency as well as voltage. So we can have this picture. This part you can see now, it is your generator here. This is generator which is rotated by your turbine, and turbine here may have the different stages. It may be your HP stage, it may be your LP stage. Basically it is first IP, then it is LP stage, and the steam is coming here, and which is that steam is giving energy in terms of rotational energy, and then here your generator is coupled. Now this generator will giving supply through your here generating transformer, and finally it is going to the grid, and or you can say network. So this part you can say your left hand side starting from here, we saw this is nothing but it is your ALFC loop, that is a automatic load frequency control loop, and already we model the primary ALFC loop, and then also we saw the secondary ALFC loops. So to see, visualize physically what are the components those are acting here in your secondary ALFC loops, or you can say complete this automatic load frequency control loop. Now you can see here the system frequency here, this is your network, and it is going to the here your this grid, or you can say connected with the main system. So the frequency which is here measured by the frequency sensor, so this is your frequency sensor, and this is giving your F, and now finally it is coming here in that. Also here we are measuring the tie line power flow. You remember that we require the tie line power flow as well as the frequency when I was discussing about the AGC logic. So here we are measuring the tie line power flows, means the area where they are connected, what are the various tie lines, and then it is a mixed signal. Finally then from here this block is nothing but, if you remember, it is giving your area control error ACE, if you remember in the previous lecture. That ACE is integrated because we have to use the integral controller, so that's why it is written here the integrator. So we use the integral controller to reduce the error in terms of your frequency and your tie line power flow. Then it is to do this, what we do, the speed changer, that is the input to the speed changer, that whether we have to increase or decrease, it depends upon what is the input coming here, and that it is decided by your ACE, that is a area control error. So speed changer command will be given, then this command is passing through your governor. Here the governor, already we model the governor along with the time constant and the governor gain, and then it is coming to some hydraulic amplifier here basically, and then it is turbine. So whole this block, basically this block we model completely in one. Here a governor, then we model the turbine. Here also we can see that we are just sensing the speed, and then we are giving to the speed governing system. So there are the two things here, it is measuring your speed, thereby frequency, and then it is controlling. So this complete loop up to this part we model here in analyze in the previous 6 lectures. Now we are coming to the AVR loop. This LFC, of course, it is controlling your frequency F. Now we are trying to see what will be the control of the voltage by the generators. Now here also this system voltage that is assessed here. This voltage basically here it is a AC voltage, then we are using some rectifier and the filter circuit, and then it is giving your V magnitude at that terminal voltage, and once it is compared with the reference value here, the voltage reference is compared with the comparator, and that error, change in the voltage error, is given to amplifier. That will amplify because this magnitude is very, very small, and after amplification here it is going to your exciter, and this exciter is providing the field current to your alternator here. This is basically a field binding will be there, and it is doing that. So we can also sometimes give some auxiliary signals to the exciter. It is not only voltage, we can give some other signal, we will see later on. Then here we can give some auxiliary signal, and then it is called some power is given to you. Now here this exciter, as you know, it is also requires some power, and that power basically comes from this rotor. So normally this exciter is rotated through this rotating body of the turbine here. So we give some input power and we will see the model. So now we will model here this amplifier, we will model the exciter, we will model here generator, and then using whole this loop, it is a one loop, it is called voltage control loop, or sometimes called AVR loop, sometimes also called here the excitation system of alternators. So here now we are discussing the voltage control. It is the part of alternator. We will see there are other devices in the system. They are also trying, they can control your reactive power and thereby the voltages. To see that, here let us see what are the various generation and the absorption of the reactive power sources in your complete electric power system. Electric power system, once again I want to repeat that electric power system consists of your generators, transmission lines, and the distribution systems. So it is a complete, so where who are going to generate reactive power, who are the elements those are consuming reactive power, that we are going to analyze here. Then we will come to the sources and then we will describe accordingly. First element here, of course, no doubt we start from the generators, but I will discuss generator later on. So we have to start first, another is your transmission system elements, and the transmission system elements are normally here, they are these three. Means the transmission of power is carried over on the transmission lines through the transformers and the cables. Transmission line here, they are called that they can generate reactive power and they can also absorb the reactive power. How they can generate and how they can absorb, it all depends upon the loading of the system. Why I am calling this? Because a transmission line, if we can model here, this is your transmission line reactance, then it will have some resistance, and let's suppose I am modeling as a pi equivalent. So here what will be that? This will be the charging capacitance. Here let's suppose a pi model. This is grounded and this is between bus I to J. Now whether it is this whole element is generating or absorbing, it depends on how much it is consuming and how much it is generating. Now the consumption here, let's suppose this current is flowing I here, and the voltage here, let's suppose the V constant at all buses, that is your sending end bus and the receiving end buses. So I can say the reactive power absorption is your nothing but your I square XL will be your reactive power absorption. But you know, these reactors are the good source of reactive power absorption. The capacitors are good source for generation of reactive power. So these capacitors will try to generate, and they will, what they will do, they will generate here X square upon Xc. Here Xc is including both. So now it depends the reactive power here Q, whether it is a positive or negative. If this value is negative, then we can say this is generating reactive power. Means if this minus this, means this is loss, this is generation, means absorption minus generation. If this value is negative, then we can say this transmission line is generating reactive power, or if it is positive, then we can say this transmission line is absorbing reactive power. How come? You can see there are the two elements, the voltage. Voltage is normally the operating voltage or variation is very limited. Means it will only change plus minus 5% or maximum plus minus 10% in the lower voltage system. But the current, it can go from 0 to its full rated value. So this value varies quite high, it's quite more compared to this. This is almost constant. So whole this Q basically depends upon this current I. And that current I, you know, it is called the loading of that line. So if this transmission line is highly loaded, there will be possibility that this component will be more than this, and finally this will be positive, means this will act as absorption of reactive power. Similarly, if line is lightly loaded, very less value, let's suppose this is 0, this will be your negative value is coming. So in the light load or no load condition, once line is energized, then what will happen? This component here will be your, I can say it is QL, here I can say QC, and this will be your condition or that one. So under the light load condition, this is the condition when the light load condition means the transmission line is loaded lightly, light load, and this condition when it is a heavily loaded, a heavy loading condition. There is a possibility that both this Q loss, that is a absorption, will be equal to your Q generation. Then what will happen? Your Q will be 0, and that condition is called the flat line. Means when your total power generation and your absorption is matches together, means there is no reactive power generation or loss or absorption, then it is called flat line, and the voltage throughout this transmission line will be the flat and it is constant. If you see the voltage profile here, let's suppose the voltage at these two ends are fixed and these are value as your V, then the condition here that voltage will be like this. Here you can say Vi, here it is your Vj, magnitude I am talking, and there is a possibility that voltage will be like this or voltage will be sagging like this. So this will be the condition when your I here is more, means this condition when your QL is more than your QC, because it is going to absorb and the voltage will fall. So voltage will sag, you can say the voltage will be lesser here in the mid of the line. Here the reverse is true, means here basically your I square XL here will be less than your V square upon XC, and this is called light loaded condition. So you can see the voltage profile between the two nodes. If the voltage are fixed, it will be changing depending on the current which is flowing through these transmission lines. So we can say that transmission lines can generate or can absorb reactive power, and it all depends upon the loading of the line. Normally this charging is very predominant when we are using very extra high voltage transmission line, and also if the line length is very large. For the short transmission line, this value is very less, and always there will be either flat or it will be sagging nature. So all we know that the transmission line can be categorized as a short line, medium line and long line. Especially for medium and the long line, we can have all these type of possibility. So this transmission line can work as a generator or work on the absorption of reactive power, means both it can do. Now let us see the transformers. If we will draw the transformer equivalent circuit, the transformer equivalent circuit, if you will see here, I can simply say, if we are some part is ignored, normally this is simply a transformer. Although there will be some shunt part, and that shunt part are basically denoting your this core loss as well as the magnetizing loss, and that if we are ignoring, then we can say it is a simple your XL. There is no capacitance at all. There will be some resistances, but this XL of the transformer windings are very high compared to the R. We can even ignore that resistance as well. So you can say this is a perfect inductor. So in all time, in all the cases, whatever the loading is, this transformer will work as a reactive power absorption. So the transformer consumes a huge amount of reactive power compared to other elements in the power system. No doubt the reactors are also some sort of transformers. Simple windings are there. So they are also absorbing huge amount of reactive power. We will see later about the reactors. Now the transformers again can be of the different type. The transformer here, as I said, we can have some transformer with the type changing positions. Means it is called, let's suppose, your off load tapping transformer. Means normally some transformers are provided with the some tappings. Whenever the voltage is going to be less or higher, we can change the tappings and then we can increase the voltage or so. So what we are doing with the changing of the tapping, it is nothing but we are trying to provide some reactive power. For example, this is your line. With the help of tapping, some fictitious if you can model, here we are providing another device, here we are providing another some sort of generation. So one end it will be working as an inductor and one end it will be working as a capacitor. But addition here is always 0. So by changing the tappings, let's suppose you are increasing the tapping, this will work as a capacitor and it will try to increase the voltage of this end. However, if you want to go for the lower, then it will work as an inductor and this will work as a capacitor and there so on and so forth. So it is called off load because we cannot change the tappings during the on load condition, because if you are changing the tapping, for example, let's suppose here you are having a tap, here these are the various taps, and suppose here just we are having right now and it is your connected, this is let's suppose your primary, this is your secondary, you are just changing from here one position to two position, there is some open circuit and that will be huge transient will be generated. So what we do to avoid that, and also there is a huge voltage here difference between these point 1 and 2. So what we do, first we de-energize, then we move the switch 1 to 2 and then we can again energize. So it is called off-load tapping position at tap changing transformers. And the tapping change, by the tapping we can change the voltage of that end. Either we can increase the tapping, voltage will increase, we will decrease the tapping, then again it will decrease. Another transformer here, since it is not always possible that to de-energize the transformer or then go for the tapping, because again that will create another problem because your supply will be interrupted. So if your transformers are small and other things, then we can go for the interrupting a small load. But if we are working about the big transformer and the power transformer, those are you can say interconnecting transformer ICTs connecting 400 by 220 lines, it is not possible to de-energize and then change the tapping. So for that, normally we have the online tap changing positions. As you know, online means that is sometimes called on load tap changing. So here it is called OLTC transformer, tap changing transformers. They are used, and here we try to do in a such a fashion. Again, the purpose is same, that we can change the voltage by changing the tapping of the transformer. For one example, I can explain you how they are done. Let's suppose you are having here the transformer winding. Here we are having also some binding, and there the different tappings are there. Here you can see. Now what we do here, we have some 180 degree here, there's 90 degree displaced bindings are there, and then let's suppose we are having positions here as well as here. Now this is your position 1, you can say right, it is position 0, here 1, 2 and 3. What will happen, this is now only this binding is coming into the picture and the voltage is there. If you want to change the position from here 0 to 1, we have to, again as I said, if you are suddenly changing, there will be huge spark and there will be possibility of the breakdown of the insulation. So what we do, we normally put here with the some switches S1 and S2. First what we do, we open this, then we change here. In that condition, what will happen? You can open this and then you can change here, however it is connected. So in that condition here, there is some mismatch in the voltage. Here this voltage is added here with this voltage. So that amount is very, very small, no doubt. So, but once you are here, you have moved here, then what you can do, then you can open here, you can close this, you can open here and then you can shift here. So in one operation you have to open and close. At least 6 and 8 operations are required, and then we can move in this second to position, and there is no need to de-energize, means in working condition we can change the tapping. This is called your online tap changer transformer. Another transformer is also called the booster transformer. Booster transformers are basically nothing but, if you are having a transmission line, let's suppose here, this is a transmission line. If anyhow we can change the voltage, we are injecting a series voltage in the transmission line here, and that value basically coming from somewhere here the transformer, and we are having some tappings here, you can say different tappings voltage we are adding. So this voltage here, this end, basically we are adding with this VI here in this phase, and then here it is called the boosting transformer, means voltage at the J, here it is your I, will be nothing but your Vj will be your Vi plus change in the voltage I, and then the voltage is boosted. So this is basically called the booster transformer, to again change the boosting the voltage. This is here we are adding the series voltage in the transmission line to increase the voltage control. Another device here, as I can say, another device is your cable. We know that the difference in the transmission and cables, the transmission is having the wires 3 different phases. They are quite apart. Almost it is a 4-5 meters at least. They are 3 phases are allocated. So what happens? The distance between the phases are very high. So the capacitance formed here, this value is very less. However, in the cables, they are very close to each other. Again, they are insulated by thick insulators, but they are very close, so the charging value is very high. But at the same time, inductor value will be very less. We know that the distance, you know this L here, how it is related with the distance. You know this capacitor here, it is your 2 pi epsilon naught upon ln d upon r. Here we know the 2 pi into 10 power something into ln d upon r. This is some factor here we use. Now if the d is more, L will be more. So in this transmission line, d is more, larger, then what we do? Here we get L higher value and C is smaller value. However, in cable we will get the reverse here, C higher and L lower. What happens here? Whatever the loading, this XL is very small. This value is very small because the C is very large. So the cables normally they generate huge reactive power, and that's why you can say the cable we cannot have more than 50 kilometers cable, because what will happen, a cable if you are having more than certain distance, normally it is 50-60 kilometer, here there is load is 0, you will be getting here the I full rated current. Means if you are increasing the load here even the fraction of megawatt, this line will puncture, this cable will puncture. So we have to go for the smaller distance cable, and that's why the DC is proposed. Suppose you want to have a bigger cable than required, that suppose you are connecting two islands, they are, let's suppose, 100 kilometer apart. So what is the option? Only the DC cables. So we have to have the DC transmission for that. So these are the problem in AC, already I have discussed in the very beginning. But the cables, they are normally only generate reactive powers. They never absorb whatever the loading will be. Another device is capacitor. Again, the capacitors are used very widely in the distribution system. Again, they can be connected in the shunt of the system, that is connected to the bus, to the ground in between, or they are connected in the series of the two buses. So if they are connected as a shunt, then it is shunt capacitors, and other are series capacitors. Now let us see how we can analyze them. Now this capacitor here, what I am going to do, this capacitor, if it is connected, let's suppose here this is your transmission line, we are connecting a capacitor here, and this is your ground. So this capacitor is known as a shunt capacitor, and as you know, this shunt capacitor means it is shunted from bus to this. Series capacitor, however, this it is a transmission line, and then we are connecting here, and this is your, I can say, XC, here it is your XC. So this is series, this is your shunt. Again, the purpose of these two connections are different. Normally, if you are connecting the shunt here, if the purpose is to improve the power factor, or to inject the reactive power here, and to improve the voltage profile of the system. If voltage of this system is changed, there will be the possibility the voltage of neighboring connections, they will be also affected and they will be modified. So the putting this, what we are doing, we are meeting the reactive power requirement locally. If the, let's suppose, load is here connected and it has a poor power factor, so the reactive power will be provided here. We don't require reactive power that flow on the transmission line. So the reactive power support provided by shunt capacitor, let's suppose for same value, let's suppose C value is your 1 microfarad. If you are using as a shunt for same voltage here bus system, then the reactive power support here QC, it will be larger than QC supplied by the series here. So always, if your intention is to provide the reactive power support, you have to use in shunt. Here XC is provided to compensate the reactance of this line, and then what happens, by this XC we can go for more loading of the transmission line, because you know this loading of the transmission line is nothing but here what I can say, it is your P, it is your V1 V2 upon X sin delta. Delta, or you can say delta 1 minus delta 2, that is a change in the here bus 1 and here. Now this X, if there is no capacitor, this is your simply XL, that is a inductance of the line, this reactance omega L. So what we are going to do, if we are putting this Xc, then here I can say minus Xc will be there, and this value is now reduced. Then the power flow over this line is increased. However, the power flow control effect of this capacitor is very, very less. So now I can summarize here, putting the shunt and series capacitor means your shunt capacitors, here I can say shunt capacitors, and here your series, here it provides more reactive power and here it provides less reactive power. First difference here. Second, here it increases the power flow over the transmission line. Here, it is impact is less, so I can say less power flow control. Here it is more power flow control over the line. Also here the insulation level, the third comparison, if you can see the in series here, this is if line is 400, then you have to provide this capacitor of the 400 insulation level from here line to ground. So they must be protected very carefully, and the insulation level must be proper. Here no doubt this one end is grounded, here is the high voltage, and we have to go for that. So normally if this capacitor is short circuited, there is a huge transient and other problems occur. But here if short circuit, this will no doubt this will work as a fault. Here this will not work as a fault. So we can compare and we can go for the advantage and disadvantage. We will find the application of these two type of capacitors are different. Here for the voltage control, always we go for the shunt. However, if we want to control power in that line, the series option is better. So another device that is very popular, and it is used especially in the extra high voltage system. It is never used in the distribution system. However, the capacitors are very common in the distribution system. Always we try to meet the reactive power demand locally, because your loads basically they are the good source of reactive power consumptions. So they are basically, that reactive power must be met locally to take care of that. Another is your here your reactors. Again, the reactors, as I said, they are nothing but here these reactors are normally connected at the bus. Here this is your transmission line, and the reactors here you can say simple here reactor, and it is just looking like a transformer if you see. So the reactors are basically used in the transmission line whenever there is excess voltage. When do you want to charge the reactive power, and that situation occurs especially when your loads are light, means lightly loaded transmission system. At that time the lines are generating reactive power, and the possibility of the getting voltage of these end will be very high. During that condition, means during the light load and the no load conditions, we normally put the reactors, and the reactors can be categorized, again depends upon the location, will be the different. So first one is your line reactors. They are basically the permanent connected reactors. Here in the lines they are connected, here these are reactors. So at the both end of normally of the line, the reactors are connected. These reactors here, they are called the line reactors, and the purpose of that, they will absorb the reactive power, and whenever there is some switching transient, dynamic over voltages, they will try to reduce that. So they are used to reduce the dynamic over voltages as well. Another is your bus reactors. Bus reactors here normally, this is your bus. Here normally we use with some switch, and here that bus reactors are there. These bus reactors are not permanently connected, means they are normally in the off condition, and whenever they require we can switch in, and then we can switch it out when they are not required. So this is your bus reactors. They are connected at the bus, and normally they are connected in the substation. So this is your bus reactor. The primary objective is to maintain the voltage. When suppose your line is going to be energized, this is your circuit breaker, your line is, let's suppose, off condition, you are connecting your line, there is a possibility due to the Ferrand effect, the voltage of receiving end will be higher than the sending end, and then there will be the cascade tripping if are not reducing the voltage, because the relay will pick up. High voltage, over voltage relay will take care, and then again it will be de-energized. So we have to put all the reactors in the system, then we have to energize the line. We have to connect the line with the synchronous system. Another is your tertiary reactor. there is a possibility that here we are having a transformer, and this transformer will have another tertiary winding, and if you are connecting here the reactor in the tertiary winding with the some switch here, then it is called your tertiary reactors. Why we are going for the tertiary reactors? The main concern of these reactors that these reactors are rated at the line voltage here. This is the voltage of the bus. So here the insulation level and the cost is very high. But here what we can do, if the tertiary winding, normally let's suppose we are using here 400 by 220 kV transformer, and it is having a tertiary winding of 33 kV. So this insulation level of this reactor is very, very less, and then it can provide this reactive power absorption whenever required. At the same time, this tertiary winding can absorb the reactive power, that is a triple N harmonics current in that, and where can be circulate here. So this is your tertiary winding. So this bus reactors and their tertiary windings reactors, they are used especially when the overloaded condition. But the line reactors are permanently connected in the lines. Whenever it is energized, it will be connected. It is immaterial what is the loading of the system. Nowadays again we are feeling there is a huge surge in the voltage, means voltage variations are very high. So now we are talking that why not we can put some reactor with some thyristor, we can put some TCR, thyristor control reactor, that is called TCR, means we can control the reactance value. Why sometimes unnecessary we are trying to reduce the voltage, so that we can maintain the voltage here to any control value that is a specific one per unit. But putting these thyristors, the cost will increase, and nowadays in several places in ITRC here in India, we are having the TCR rather than simple your inductor, that is reactor. So that is also possible. Another, that is a reactive power consumption or generation, we can say. So this device always absorbs reactive power. Inductor always absorbs, capacitor always generates. If combination of that, then we have to see what is the condition, which one is higher. Now another, that is before going to the synchronous machine, I will just discuss about the loads. Loads here you can see in a whole system. What are the loads are available? We can go for the lighting loads, and another is called the motor loads. So the loads can be categorized into two ways: the motor load or lighting load. Some loads are also there like arc furnace, that is a heating load. So we can also go for the heating load, but mostly this motor load is accounting for almost 70%. Almost this 20% of this load, and the remaining load here of the other purpose like arc furnace, heating purpose, heaters, etc. So the motor loads are the more, and the motors widely, there is two type of motors. AC motors are available, that is your synchronous or it is induction. In the most of the condition, you know, we use the induction motor because it is a very, very versatile, rugged and reliable. So we use the induction motor, and you know the induction motor is nothing but it is just like a generalizer transformer. A transformer consumes reactive power. So this consumes reactive power every time if you are using the induction machine. Here induction motor I am talking. If you are using synchronous motor, no doubt you can operate in this both leading and lagging condition, means even though you can generate the reactive power. But the induction it is not possible. Every time it consumes reactive power. Lighting load again depends upon which type of lighting you are using. If you are using simple bulb, power factor is unity and it is not neither consuming nor generating reactive power. But if you are using the fluorescent lamps, another type of lamps, what happens? Here in the CFL, they consume huge amount of reactive power, and that here that again comes to in the picture. So the loads mostly, if you are going to add all the loads also consumes reactive power, means you are adding all the loads. I am not talking about the single load. If you are adding all the loads, then this is work as your consuming reactive power. Another device in the system, that is your machine, that is a synchronous machine. I said synchronous machine. Why I am writing machine, not generator? Because the machine can be it can work as your motor or it can work as a generator. The difference between motor and generator we know it very well. Means if you are connecting three-phase AC supply to a synchronous machine, it will work as a motor and it will do the mechanical, that is rotational speed it will give, it will do the mechanical job, and that electrical energy is converted into the rotational energy. In generator we rotate it and then we get the electrical power. So in the machines, now what normally we can go for, here this is your machine, now it is connected with the system. If the power here it is going to the system, it is called your generator. If here this is your synchronous machine and the power coming from the system, you can say it is a motor. Now the reactive power expression, this P, that's I am talking here about the P, here it is your P. Q can be anything, as I said, Q can be your negative and positive. It is the optional in the machine that we can either generate or we can absorb with the synchronous machine. This is the beauty of this, and this is only possible because we are having doubly excitation system. Synchronous machine, it is a single excitation because only AC that is coming, but in the synchronous machine we provide the DC excitation along with the AC excitation. Means there is a two field of difference, so it is called doubly excited machine. So here the power is injected to the system, and here we are getting power, then it is a motor, here it is a generator, and then we can use the synchronous machine. Now the reactive power, that Q, is related here in this machine, then it is again expression is true for both here as well as here. And now if you write here the Q, and this is also Q, if this Q is positive, that's expression I have written, Q, that is reactive power, that is E into V. E is your internal voltage, V is your terminal voltage, divided by X in between the reactance, that is the reactance of generator. Cos delta means delta is angle between this, here let's suppose is 0, here we are having E angle delta, so this is angle, and V square upon X, this is expression. So this value can be positive, this can be your negative. If this value is positive, then for the generator case we can say it is generating reactive power to the system, means it is generating here. If here this value is less than this value, then we can say it is absorbing reactive power, and this is coming here. Now again this leading and lagging concept we can decide, and we can just I'll explain you how it will be the leading. If P and Q, I can say P plus JQ, I can say it is lagging. If it is P minus JQ, I can say it is leading. So the V curve is one approach by which we normally say whether it is a leading or lagging. Okay, let us see the leading and lagging. Normally that is decided by here your, it is known as the V curve, that is very popular. Here if you are the field current, here if you go for the field current IF, here I can say your armature current, if they are going to be related, then we normally get a V curve here like this. So again the whether it is a leading, one side it is leading, another side is lagging, and this here IF is directly proportional to E, we will see later. So if IF is more, means this component is more than this, then it is a positive, and in the generator case it is called your lagging case, and this one is your leading. So we operate the generators in mostly the lagging case of the generator, no doubt. Remember here lagging for the generators. However, for motors, why here the lagging you can see the P plus JQ is there. For the motor the lagging will be only because the P which is coming out minus JQ. In that case what we require? We require the Q here in the different direction. Here this will be less than this, and then we can say here is a lagging, and here it is your leading of the motor. So this motoring case here the leading is required because we can generate the reactive power. So in case of motor, here if write motor, so motor here we want that for the reactive power generation it must operate in the leading power factor mode PF, then it will be generating the reactive power, means reactive power injection to the system, it will try to inject. However, for the generator if you are operating the lagging PF, then it will, the Q will be injected in the system. Reverse is also true. and it all depends upon what is the value of E here. Normally the delta, as I said, delta is decided by the power flow. So only this E, which is the excitation voltage, and this field excitation decides the reactive power of the generator, as I have written here. So this E can be controlled in a such a fashion that we can make this component more than this, or we can make this component less than this, or we can make it equal to this, then it will be 0. So this E control is basically called the excitation control of the system of your loop. In other here the devices which I explained earlier one, there was no control. If you are not using any other extra power electronics devices, because if you are, for example, your reactor, once reactor is connected here in the system, then it will be providing the reactive power support, means here it will be absorbing reactive power from the system. Now you cannot have control. Here your this Q, L, this of absorption will be nothing but your V square upon this reactance of that inductor. So XL is fixed, omega is fixed, then V, the voltage, whatever the system voltage will be there, it will be absorbing. You cannot control. Similarly for the capacitors, similarly for the load. Load can be changed because the motor load will be the different, then reactive power consumption can be changed, but we normally never control because the real power is fixed. Transmission line, here you cannot control the parameters. Parameter XL and other things are same, and the loading you can, of course, can be changed, but it is not in our hand because the load are keep on changing. So the only the control option which we are having, either we can have the reactors with the some controllable devices. For example, as I said here, let's suppose we are having some firing angle control and we can change the reactance here. Similarly, the capacitance can be changed. Then it is another device which is called flexible AC transmission systems, FACS devices. Means we are using any power electronic devices that is known as flexible AC transmission systems. Then we can control. Otherwise, it is not possible. All the devices are the passive devices and they are fixed, so you cannot control anything. Now this machine here, without any other things, we can control the power, we can control the voltage, and the voltage basically is controlled by the reactive power, and this reactive power can be controlled by this E. So this E is basically sometimes denoted as EF, that is called field excitation or field voltage. And that is basically controllable quantity, as already explained in the first slide, that this is your field voltage, we have to excitation, we have to control. And that is the field binding of the generator, that if we are changing the field current, this EF will be changed. No doubt in the generating stations or generators, we are having the different type of excitation system, with a very classical conventional excitation system, having your rotatory type excitation system, having some DC type excitation system, we have the static excitation system, and also we are very popularly known, that is a brushless excitation system. To have this, let us view one excitation system which I am going to show you. It is your brushless excitation system. Why it is called brushless? Because we are not having any brushes here in the excitation system. One thing you must be very aware, because here your generator, this is your big generator. What I am saying, this is your generator, this is the armature binding is on stator. So we require some rotating part. So your rotor which is rotating here. So the shaft here which is connected here, that is rotating. So your field binding can be on stator or it can be on stator. But your armature binding normally we keep on the stator. It has several advantages, we know it very well. Because for higher voltage, the rotating brushes etc. is very, very difficult and very difficult to manage. So normally, since we are going for very huge power, sometimes 500 megawatt power, megawatt, MVA you can say, or it is voltage is sometimes 21 kV, very high voltage. So on the stator, once it is static, we can provide the good insulators, means insulation between the windings, your core, so your yoke. So all of it is very easy and also very easy to cool it. So always the synchronous machines here, generators, we put the armature binding on the stator and the field binding on the rotor. Now if you are having the field, basically we provide here the field, and then it is rotating. So if you are having the rotating, means you should have some brushes here to make it rotation, and that we don't want, because the brushes, there will be a lot of contact, carbon problem, sparking problem, but bursting up this one, and reliability will be very poor. So another is called your brushless excitation system. Let us see here, that I am going to explain you. Now this is your, as I said, you will start from here. This is your synchronous generator, or it is also called synchronous alternator, or simply alternators. They are here generating your three-phase supply, your VA, VB and your VC, and we are having the armature binding here, A binding, B here, and your neutral. Just we have shown it is a grounded. The armature is on your stator, as I said. Now your field binding is on rotor. To avoid this, if you can rotor on itself field binding there, and it is keep on rotating, so then there is no need of here the brushes. If it is rotating field binding, so here you can see the field binding is rotating, and this field binding we require the DC. You also always very careful. Here we are getting DC, AC. We are providing the DC supply to the field. It is a doubly, as I said, here not AC and AC, it is a DC and AC. So we must provide the DC, and where we can get DC? It is not possible that we can provide from the batteries. So what we do, we can have another generator, and that is rotating on the same speed and mounted on the shaft here, and then we can use some rectifier. So you can say we have a rectifier, you can say bridge rectifiers, three-phase. This is all the diodes, or you can say we can control also if they can be thyristors. So here is a field binding, and this is armature binding of exciter. It is also a simply alternator. This alternator is again rotating. So what we have done, this exciter here, the armature is rotating, its field is static. Means now we are putting the winding on armature on the rotor, and then here we are generating three-phase, that is we are here the rectifier, and finally we are getting here the DC current, that is the field current, and this field current is generating your field voltage, and then it is generating your EF, excitation voltage. Now since it is another alternator, it is no doubt it is a small power, because the field power is very, very small. So this rating is very small, and then we can go even for your armature bindings on your rotor, and here the field binding is on stator. That field binding is now getting supply from somewhere. So what we are doing here, we are having some CTs and PTing. Now we will come later this part. Here we are just the potential transformers are there, and then we are just using filter and rectifier circuit. We are just getting the voltage. This voltage here we are comparing here, this is your comparator. Means comparing this V reference, what we want the reference voltage of this terminal voltage. To have this, we are comparing the actual voltage, and then we are just comparing, and this error signal is given to an amplifier. Now for this sake of simplicity, you should forget this GS and GF functions. Normally they are used, and they are called the stability compensators. This is a feedback gain, and this is a series transfer function gain. Because we try to stabilize this loop, we will see later, this loop is sometimes very critical, it may not be stable. So we have to go for some compensator. But normally if they are not there, so simply it will be your, this value is coming, and this is not there. Don't consider this. Then what is happening, this error is coming to your amplifier circuit. This amplifier is used because the error signal is very small. We require the field current that requires some power. So that here field current is this amplified, and then it is given to your field binding of this exciter. The other energy, the energy here for the field binding is taken from your rotor which is rotating. So energy from rotational we are getting, of course, but we require some field current as well here, and that field current is coming here, and that it is again it is rotating. So you can see whole this part is on rotor, and there is no brush, and that's why it is called brushless excitation system, and it is very widely used, brushless excitation system, in machines, alternators. Now to see whether this control loop, that is a automatic voltage. Here AVR is your automatic voltage, sometimes called regulator loop, so AVR loop, or sometimes called excitation loop. So this is whole one loop. You can say some feedback is there and keep on trying to maintaining this voltage to its reference setting. Now to see its performance, to see whether we require some stability compensation devices or not, we have to model each and every component. We have to model amplifier, we have to model the exciter, and we have to model this synchronous alternator dynamics. The rectifier dynamics is very fast, there is no need to model. So we can directly take this current here, and we will see the time constant of rectifiers are very, very small compared to the other, because this is a rotating mass. Here also some rotation part is involved. Amplifier, we require some gain to amplify, and that gain is sometimes very, very critical, and then we have to decide what should be the gain, and we will see the stability and the accuracy criteria are conflicting together, and then we have to go for some compensating mechanism, and here maybe your series compensation or some compensation, you can say feedback compensations are required. So to start with the modeling, the major objective of AVR loops are to maintain the static accuracy of terminal voltages, and also to have the better transient response, and the transient response in terms of it should be stable, and also it must be settled in reasonable time. So the settling time should be less. So first component, as I said, is your amplifier model. Amplifier may be any time, it may be amplitude amplifiers and so on and so forth. And we can have the first order amplifier model, and here I can say the transfer function of amplifier, that is a GA, it is nothing but Ka, that is a gain of amplifier, over 1 plus STA, and this TA is the time constant of amplifier. We will see the time constant of the amplifier later on. So we can have the first order model of your amplifier, and it is available in the several literatures, and then we can say this one. So what will your VR? From here again you can see this is your VR voltage. This voltage here, that is coming, your E is coming here. So E multiplied by GS, we are getting VR. So I can say simply here, so VR will be your E, that is error signal. This error signal is nothing but it is the difference of your reference minus your actual terminal voltage, this is that one, and then it is multiplied by the transfer function of your amplifier. So we can say here, we can write in this VR, that is a excitation field voltage here, exciter field voltage, not generator field voltage. Here VR is the GA multiplied by EA, or in difference form, if you are talking about the small change, we can write change in the VR is equal to your GA into ES, and this is your one transfer function model we will see, and then VR we can relate it. So next component is your exciter, and now we have to model the exciter as well, and now we can assume that the field is having your RE and LE, means if you will see here in our previous case, this block diagram, this here value is having RE and the LE. LE is the inductance and RE is the resistance, and then we can write here the voltage equation, means I can write this VR will be nothing but your RE IE plus your LE DIE upon dt. So this we can write this differential equation. For this VR we know we got from previous stage, and this here we can write a equation in terms of time derivative. So from here what we can do, we can now come to this, what is the change here, we can write as I said VR is equal to RE multiplied by current in that excitation field, LE into the differentiation of your excitation current, field current here, divided by dt. So we can take the Laplace transform then, and we can simplify, means we can write here it is nothing but your VRS will be equal to your RE plus here your LES, and we can say it is your IES here, this value will be coming. So from here we can take this, and VR upon IE is nothing but your RE plus LES. S is your Laplace S variable. We also know this voltage, that is a field voltage, which is we can directly write that the VF will be proportional to IF. This VF is nothing but your, it is IF, means whatever the current which is coming here, that is your, is related with this, proportional to this. I can say this VF is some constant KF multiplied by IF. Now this VF is, will be equal to your I1 into RF. Why? We will again coming back to this, see this picture, sorry, this picture, let us see the again black diagram, bigger one here. This VF and IF, this voltage here related, they are basically directly related here. What will be the current here? We can relate this VR with this one, IF, and IF is basically proportional to the VF which is coming here. This time constant is very less, negligible. So I can say here this transfer function, that's your VF will be, in other terms, it is terms of your IR, that is a current here, and then we can replace the value from here and we'll get this value. Means we can put the K1 here, we can put this IR and we can get this value very well. Okay, so here VF, yes, here it is your E basically, and this E we can replace from here in this equation, and then we can get K1 upon RE plus LE VR. So now we can say it is your, here VF upon, I can say VF upon your VR in S domain, here it is your nothing but your excitation transfer function, and now I can say here this K upon 1 plus STE is your the transfer function. Means here it is nothing but your K1 RE plus LES, or we can say if we divide RE in both way, I can say K1 divided by RE over 1 plus LE upon RE. Yes, what is this LE upon RE? It is a time constant here, thus I said is a time constant of excitation winding, field winding basically, and this is some gain. So we can write the transfer function of this here, your excitation winding. Now after that again we have to model this excitation. We have modeled the excitation, now we have to model the alternator, and that we'll discuss in the next lecture. Now I can recap. In this lecture we saw the various sources and sinks of reactive power generation and absorption. We saw the transmission line, cables, load, reactors, capacitors, transformers, and also we saw the synchronous machine, that is your alternator and the motors. Then we started with the AVR loop, that is the automatic voltage regulators loop or excitation loop, and then we model amplifier, excitation, and next we will model the generators, and then we will come to a complete loop, and then we will analyze the behavior, means static as well as the dynamic response of that loop in the next lecture.